Yeah, hello, I'm Michael. I'm a PhD student in the group of Philip Gross at the University of Vienna. And I want to tell you a bit more about what we do with neural network-based wave functions. So we've already had a few really nice talks about the topic, in particular also like Jan Herman and Matthew Folks, who have already demonstrated that we can reach extremely high accuracies, right? You might have seen in the talk from Matthew Folks yesterday that if you want to calculate energies of small molecules, in many cases, deep learning-based variational Monte Carlo is actually the most accurate results you can get. And we'll show you some more of that in my talk as well. And also we've shown that in principle, right, there's favorable scaling. In principle, these methods, compared to other highly accurate methods like CCSTD, we get scaling that should be something like the order of n to the fourth. So that's nice. But kind of the dirty little secret is that the prefactor for the computational cost is actually really terrible. So even if you do a small molecule like benzene, if you want to properly converge that will often take hundreds of thousands of optimization steps in BMC, translating to something like weeks of GPU time, which makes it not really feasible to apply this yet at kind of larger scale or kind of apply it in practical systems. So what I want to talk about today is what we do in our group to improve performance of these models. And I want to pick out two distinct topics. One is, what can we do to improve performance like for a single molecule? Just if you want to know the energy of, let's say, benzene molecule, what can we do to like cut down on the cost, but also at the same time, hopefully improve a bit the accuracy? The second part I want to talk about afterwards is, what if you're not only interested in a single molecule, but many different molecules, right? There might be many applications, might be because you're interested in some potential energy surface, might be because you want to generate a training set for some kind of supervised learning method. What can you do there to kind of not have this extremely high cost many times? So I think we've already had extremely nice explanations of deep learning-based VMC, so I'll not go through it in as much detail. But just to kind of bring everyone on the same page, what we do is standard VMC. We do it in first quantization, and we do it for typically like small molecules. So all of our wave functions are fermionic. The systems we look at are non-periodic. We present the wave function directly in real space by some Slater-Jastrow type wave function that has neural networks inside it to be like really expressive. And then we just regularly take kind of local energy, h psi over psi. We calculate the expectation value of that local energy by doing just very standard plain vanilla Metropolis Hastings sampling, integrating the energy, and then minimizing the energy with respect to all the parameters that we have in our wave function. So the only thing that's maybe a bit special is kind of so that we use typically some kind of second order optimizers, either BFGS or KFAC, the optimizer that Matthew Folks mentioned yesterday. But then the big new thing kind of compared to the work that's been done over the last decades is that the wave function ansatz consists of deep neural networks to represent the wave function. And I want to go now in a bit more detail on how those neural networks actually work and kind of what makes them so expressive and how we can tune them to be even more expressive and also converge a bit faster. So our work is heavily inspired by the two previous works that have been done in this direction, PolarNet and FermiNet. And what they all have in common that we all start out with kind of computing some high-dimensional embedding of our electron coordinates. And what I mean by embedding is that we take some function that will be in the end in a large neural network that takes into account the coordinates of one single electron, but then spits out some high-dimensional vector, could be 200-dimensional, that somehow contains information about not only the coordinate of this one particle, but somehow also contains information about the set of all the other particles around it, so including all the other electrons and all the other nuclei. Once you have this high-dimensional representation of an electron that contains information not only about one particle, but also about kind of all the interaction it has with all the other particles, you then construct these generalized orbitals. And typically the way we do it is we start out with kind of some regular orbital, denoted here as omega, which is just a regular orbital in the sense that it only depends on the coordinate of a single electron, but then multiply by some function, could be another neural network, could also be just a linear mapping, of these high-dimensional embedding vectors, right? So kind of the one only depends on R, only on one single electron, but the other one depends on this X, which contains information about all the other particles. And the only thing that you then, and then once you have kind of these generalized orbitals, you just build regular Slater-Jastrow determinants. You can use the Jastrow if you want. You would probably also make it a function of this high-dimensional embedding vector X rather than the electron coordinates. And But so the only thing you really have to make sure is that to kind of contain the proper symmetry is that when you do this embedding, that the embedding vectors X do not depend on any permutations you have of the other particles. If you're invariant to permutations of there, then kind of determinant can take care of the antisymmetry. So then it basically all boils down to two questions. How do you now build this embedding, right? How do you kind of go from electron coordinates to this high-dimensional representation? And then what should you choose as kind of generalized orbitals to start from, which you then somehow distort by your neural network? And if you compare kind of the two big approaches that have been published very successfully, PaulInit and Ferminet, they take rather different approaches, kind of where to put the focus, I'd say. PaulInit starts from orbitals that are already like reasonably good, right? Orbitals from some CAS calculations or Hartree-Fock calculation, and then applies some backflow factor that again depends on embedding. This is reasonably small. I mean, small is still like 100,000 parameters. But if you compare it to Ferminet, they start from kind of envelopes that are extremely simple, that then in itself would for sure not be a good wave function because they are just simple exponentially decaying functions, but then multiplied by some backflow factor that depends on embedding vectors that are like extremely expressive with an embedding of millions of parameters. And we'll come later to that, and it's a good question, like what is better? Like, should you start from like a very good physical system and then do kind of minor alterations, or should you start from some very simple orbital and distort it heavily? And the way we do it is we basically also take kind of only simple exponentially decaying functions in envelopes, but we initialize them slightly different, the way that we start by doing a wave function, show in a minute. And we try to combine kind of the best parts of the two embeddings that Ferminet and PaulInit has. And I'll show in the next slide what I mean there. So how should you build an embedding? Like, if you now want to build this, which is kind of the big basic block where basically all the computational cost of your network will sit, and also that kind of in the end determines basically the accuracy you will get out, how could you design such an embedding? And on the very high level, how embedding looks like is we start with electron coordinates. We typically do some kind of minor pre-processing of the coordinates, so we can use things like distance vectors or distances, and then we run multiple rounds of kind of this embedding iteration. This will basically kind of the feed-forward network layer by layer. So what should you do kind of in each of those layers? The very first thing you might think is, well, I take kind of one electron coordinate, and then inside each kind of layer have one function or just one nonlinear layer that somehow alterates kind of the embedding of one electron and kind of layer by layer improves on it. But if you do it this way, then you don't capture any electron-electron interactions because, I mean, now you've just kind of, if you do it particle by particle, there's no interaction between the particles. So what you'll need to do is you'll somehow also need to include information about all the interparticle interactions. So instead of just having kind of this one stream that takes one electron and kind of spits out in the end some high-dimensional representation of the electron in the end, we also kind of run two additional streams that don't model single particles, but model basically interactions between particles. So we typically initialize them with something like the interparticle distance or difference vectors or some features of that, and then kind of run basically feed-forward networks to get deeper and deeper representations of that. So then the big question comes, how should you now kind of combine these two particle features to somehow get one new input kind of for the next iteration of the one particle representation? And the way we do it is in this more or less kind of message passing way that has been proposed kind of in Schnet, and also some other features very successfully, in the way that we take those two particle representations, these high-dimensional feature vectors, we feed them through some small neural network that acts basically as some kind of kernel that computes basically weights. We take kind of our one particle representations, these feature vectors X, also feed them through some small neural networks, and kind of multiply them together, sum over all the other particles. And so kind of what you get in the end is kind of some new vector that contains information as kind of a weighted sum of all the other particles you had around. Okay, so this is the way we do it. How does this differ now from different approaches? Like, how does this different from Ferminet? How is it different from PaulInit? If at first we compare against Ferminet, and now it is a bit rough, but roughly speaking, Ferminet, first of all, does not have an explicit stream to kind of model electron-ion differences directly, but kind of just pushes kind of all these electron-ion interactions kind of straight into this one particle term. That might, in some cases, I mean, it works if you do a single molecule, but might make it harder to transfer them across different molecules or different geometries. So kind of, therefore, automatically, of course, you don't have kind of these streams here, the electron nuclear parts. Secondly, fermionic does not use these convolutions, these kind of weighted sum or products of kind of feature vectors, but rather just only sums over these interactions, these two particle terms. It also just does a sum over the one particle terms. And again, maybe not a huge difference, but might limit a bit kind of how well it can capture kind of those two particle directions. If you compare that to PauliNet on the other end, PauliNet has this really nice thing of having these like weighted sum inside that might make it good to kind of capture these two particle terms. But I think there's two major differences between PauliNet and fermionic, also in our approach, in the sense that, first of all, PauliNet does not have these kind of deep streams that kind of get some really deep embedding or deep representation of interparticle interactions, but all these kind of weight kernels are basically directly functions of the input geometry, in that case, of the input distance. While kind of in our case, we have these streams that become, as you progress through multiple rounds of the embedding, become deeper and deeper, and thus also more and more expressive, and maybe allow us to get better kind of kernels to then multiply the features. The second, maybe subtle, but also I think pretty big this difference, is that like the most simple thing you would probably do if you just ran kind of a single stream is that what you want probably as an input feature kind of the next round is at least kind of have the embedding vector of the previous round as an input, so just like in the regular feed-forward network. But this is not the case in PauliNet. They don't kind of run the input of, or the embedding of the last round into kind of input to the next round. And that cuts down a lot on parameter and also a bit of computational cost, but also severely limits expressiveness, and we'll see that in a second kind of results. So that was a bit technical, but I'll show you in a minute kind of that it really makes quite a bit of difference what kind of design of architecture embedding you use for the final results.
Yeah. Your KL there.
Yes.
Sorry, I haven't read your paper yet.
Yeah.
I've been told I should. Does that mix together all the pairs of electrons?
So yes, it does, but it's like we split by spin. So there would be like two different functions, one like for kind of spins of same spin and different spin. And it's done pairwise, right? It takes as input kind of one pair of electrons, spits out some kind of weight, and then uses these weights together with the one-dimensional feature.
It doesn't consider more than one pair at once?
No, it's only pairwise. But then again, right, you run this over kind of multiple rounds. So like after the first embedding round, you've only basically considered kind of pairwise interactions. But then X already contains information kind of the one particle in pairs. Once in the next round, you already have information about pairs and kind of pairs of that pairs. So in principle, I think if you go deeper and deeper, you also capture, I think, high and higher order effects.
Yeah. Thank you.
Can I also ask a question?
Sure.
I didn't quite understand your last statement, because when we do the Schneid layers, then of course in the convolutions we convolve always with the last particle activations or the last particle features. So we do carry information throughout the convolution.
You do carry information in the sense that like you have these convolutions, right? Kind of the information about the particle kind of convolutes with kind of these feature vectors, but then you only get kind of this average representation with all the others. You don't kind of feed forward directly the input you had from the one particle. So you capture all the interactions, but you don't capture kind of the embedding vector itself.
Yeah. But I mean, it's not really obvious that this is kind of less expressive, because you can store information in these.
You can store information there, but only like in like an averaged sense. Also, if you look then, for example, at like parameter count, I mean, basically kind of, in one case, you only have kind of these interactions. The other have like interactions plus kind of the large mappings of like feature vectors to feature vectors.
Mm-hmm. Sorry, one more. What are those targets? What's in? Oh, it's down at the bottom there. I see. Sorry, yeah. I know. Okay.
Oh yeah, no, sure, yeah. Actually, like those just kind of denote these kind of convolutions of like having the element-wise product over the feature space and the sum over kind of the electron coordinates. There's a second small kind of subtlety. What you feed actually into those embedding vectors, right? I've said like we feed in the initial like the electron coordinates, and you get all those high-dimensional presentations. You could in principle do this, but you probably don't want to, because you want to like ensure that your wave function contains some geometrical symmetries as well. right? So for example, ideally, if you take a molecule and you translate it or you rotate it, you'd hope to get kind of the invariant, or that your wave function like transforms together with it, but does not give you like completely different energy when you rotate the molecule. And there's different ways how you can achieve this, but they all like have some subtleties. So for example, you can feed in just the distances so that all your wave function only depend on the interparticle distance. And that's nice, that's like perfectly invariant. But it has the issue that like you're not really expressive enough in some cases. So for example, if you take a wave function that breaks symmetry, like the excited state of an atom, if you just have an atom, if you only take interparticle distance to the atom, your wave function will always be rotationally symmetric. But for example, to get some excited state like a p orbital, you somehow need to break symmetry. And you can try to circumvent this like in the Poland approach by including some orbitals that already break symmetry. But it seems that it's still not quite enough if your embedding itself is not able to break symmetry. So that might be some kind of drawback if you just take distances. The other way you could do it is like the fermionic way, say, well, then let's not just use distances, let's use distances and also like the difference vectors. And that's nice, that allows you to break symmetry, but now you've lost any kind of rotational invariance you might have. Because if you rotate the molecule, well, all your features kind of did not rotate together with it, and so you get different answers. And there was like a nice proposal in a paper from a Munich group called PESNet, where they basically introduced this kind of depicted here in blue, like a coordinate system that they construct as the PCA of the nuclei coordinates. And so they evaluate all difference vectors in that rotated coordinate system. So this is nice because it's now like expressive enough to break symmetry. It's invariant, but it has this like maybe unfortunate property that if you had like say two molecules really far apart, and you rotate one of the molecules, kind of an entire coordinate system change, and also kind of the inputs on the other molecule will change, although physically nothing has probably changed for the other molecule. So I think you can get some somewhat undesired effects of this global coordinate system. And so what we do is we basically also build coordinate systems depicted here in orange, but we do it individually atom by atom by simply just diagonalizing the density matrix or a sublaw of the density matrix of a simple reference calculation, and then we evaluate all interparticle differences in that local coordinate system. One more trick we do, and that's especially important for heavy atoms. So if you go like to third, fourth row in the periodic table, is how you should initialize your envelopes. So we use these exponentially decaying functions as envelope orbitals. And in an initial paper by Fermi, I think they would argue, well, they're just there to basically ensure that kind of as you go to long distance, the wave function decays to 0. And so you initialize with some decay constant, basically initialize to 1 constantly. But if you compare that to an analytical solution for, let's say, hydrogen atom or hydrogen-like atom, well, obviously, the solution for like heavy atoms will be much more peaked. The decay constant will be much larger, and it goes as nuclear charge over principal quantum number. And if you initialize like that, I mean, it's just a few weights in your network of the millions of weights you initialize, but if you initialize those smartly, your calculation will converge significantly faster, and also in some cases will actually converge to lower energies. And then kind of the last trick before I come to results are two seemingly small but rather important points. One, I think that always been discussed extensively and very interesting topic is how you should deal with spin and how you should like properly antisymmetrize. So far in this talk, I've basically completely ignored the spin. What you could do is just spit out two determinants, one for spin up, one for spin down, and do the product of those, which basically amounts to having like some block diagonal structure for the total wave function. And you can do this, that's in principle fine, but there's no real reason to restrict yourself to that structure. You can also spit out like full density determinants. And I think this has already been realized in principle by Matthew and the DeepMind people, and also then a subsequent paper by Lin, that actually sometimes it's more expressive to have these density determinants. Second part, if at some point you try to like play around with neural network wave functions, really look a bit at the hyperparameters. I think since we're like in very early days, there's not really yet a consensus of kind of what optimizers, what learning rates, etc., what to use. And we find that like this can actually massively change the convergence if you just, basically in our case, like reduce learning rate a bit and so forth. Minor changes can actually get you orders of magnitude of faster convergence. Okay, so if we put all of this together, what do we get? So depicted here is for 3 different molecules, ethylene, nitrogen stretched to kind of the point where it breaks the bond, where it's like really challenging, and a potassium atom, what kind of energies you get if in the top you train fermionic for 50,000 epochs, and bottom is what you get if you train kind of our model for 50,000 epochs. And kind of every line depicts like how the energy changes, like lower energy errors are better. Since all our methods are variational, we know that kind of the lower the better. We can see that kind of what's roughly kind of the effect of different changes. So for example, if we look at the introduction of these dense determinants, in particular for nitrogen, where I have like this difficult, probably multi-reference case, there makes a huge difference. For other systems like ethylene in the ground state doesn't make a huge difference. There's some change through kind of fast optimization. So basically just since fermionic is not fully converged to 50,000 epochs yet, we get better results by tuning with the hyperparameters. But then we get like also lower our energy error like quite substantially by using this more expressive embedding. And there's like minor improvements through kind of the other tricks I showed you, these local coordinate systems, and initializing the envelopes. As you can see, initializing the envelopes doesn't really make a difference, but for heavy atoms like potassium, it makes a difference. So this is nice. We managed to like cut down energy error quite a bit, but you might argue, well, but this is only if you train like for a fixed number of steps, right? This is if you train for 50,000 epochs. I mean, how does it look if you compare about the best you can do, right? If you train fermionic or DMC or whatever you find, literally, if you train to full convergence, I mean, how does this compare?
I just want to point out that the hyperparameters in the fermionic we released are just the ones we were using for one particular system.
So you change them
statement
by
that
system?
You shouldn't change them.
Okay. Well, but this is the thing, right? If you want a new system, I mean, you can do multiple calculations with many different hyperparameters, but then becomes like super expensive in itself.
I agree. It's but it's worth trying a few different things.
Sure, absolutely. But what we found is like there is a set of hyperparameters where that like works much better, at least, let's say, and you can use the same one across a bunch of different systems. So kind of all the calculations I'll show you here are done with basically the same set of hyperparameters. So these are the results for a bunch of different systems. You can see like small molecules, small atoms, small molecule, some slightly larger molecules. How we do on total energies. So the zero line is kind of some best energy estimate we found. Could also be non-variational, I want to stress that. So the zero line is not necessarily like ground truth, but just some zero line we plot against. And then we compare against the best variation results we could find in literature. So this includes conventional methods, could be conventional DMC, could be conventional BMC, MRCI, kind of any like variational method we couldn't find. Includes fermionic, includes polarnet, like the best variation of thing that is out there. And then we compare how well do we do if we train for 50,000 steps or 100,000 steps. And we can see this basically across almost all the systems, we managed to beat kind of best existing variation methods out there in roughly 50,000 steps. And if not at 100,000 steps, this is kind of more or less done. And a lot of those kind of best variational reference we compare against are much more expensive in terms of computational cost. Just to pick a few ones out, for example, let's take neon, for example, or fluorine. So these are, I think, one is a fermionic calculation and one is a DMC calculation. A fermionic calculation ran on the order of like 300,000 epochs, 200,000 epochs with like a number of walkers of 4,000. We use half the number of walkers, a third of the number of steps, and still kind of get substantially better accuracy in that case. Or if we compare, let's say, against cyclobutadiene, I think this is a calculation as a reference, a DMC calculation using fermionic on top, kind of trained by this ByteDance group for, I think it's 500,000 epochs of VMC, then another 200,000 epochs of DMC on top, all with like more walkers. And still, basically, if you do the same kind of, using kind of our improvements in architecture and some minor changes in how we optimize, you can achieve actually superior results.
So the reference energy there is just wrong, is it? You're below it sometimes.
Yes, I think a lot of those reference energies are just kind of the best like things we could find out there, but not necessarily the ground truth in many cases. Yes, exactly. So for example, for focalizine, I think kind of or here in this case, I think most of our reference methods are like some MRCI calculations, just kind of the best conventional we could come up with. But then our BMC outperforms them by quite a decent margin. So it becomes really tricky at some point to like really find more accurate reference to compare against. In many cases, kind of your work is kind of the best reference we have to compare against, but at some point, it's really hard to benchmark these things. But it's a nice thing about variational, right? You know, as long as you're low in energy, you're like strictly better. You might argue, well, this is total energies. This is nice, but we mostly care about relative energies. And the good thing is also on this front, you can improve a bit. I don't think we're still quite there yet where we'd like to be in terms of accuracy for energy differences. But if we, for example, take here this example of nitrogen dissociation, kind of you get this like bond potential here. And if you compare the energy of a bunch of different reference methods, how they deviate from experimental values, you can see that almost all of them overestimate the energy in that region where exactly the bond breaks. So coupled clusters does quite terribly, the order of like 25 millihartry error. Fermionic already in the original paper did like much better, or 10 millihartry. If you use these density determinants and you train it extensively, you can get down to maybe 4 millihartry. And kind of using our improvements, you get down to the order of 3 millihartry. But there are like still some conventional methods, although I think exponentially scaling in cost, that at least on these small systems are like still better at predicting at least more consistent relative energy difference, right? So kind of the energy error is worse, the total energy, but at least the energy difference are a bit more consistent. So this I think is still something where like work needs to be done. Then there's something interesting we tried where we thought, well, we start kind of from these simple exponential orbitals that by themselves are like a terrible wave function. And then we apply this neural network backflow factor. So kind of we start with some wave function that's like really terrible, just exponential orbitals. We apply this backflow factor and we get pretty good results. So the question, if you start from some orbitals that are already better in shape, like not just a simple exponential decaying function, but Hartree-Fock orbitals, Cass orbitals, something like that, and you then do kind of your backflow factor on top, like surely this must be better, right? I mean, we've heard many times now delta learning is the way to go. Just kind of making only small deviations to this wave function must be much easier than kind of making this huge deviation. So what we did to test this is we start out from kind of our work. It's based on these exponential orbitals. And we try to go kind of towards the architecture of PauliNet that is based on these Cass orbitals. So at first, just kind of to level the playing field, we switch back to block-to-diagonal determinant structure that they use. We switch from kind of our embedding to the PauliNet embedding that all cost a bit in accuracy. Kind of energy error goes up. But not massively so, right? You kind of double roughly the energy error. But then we switch from the simple exponential decaying orbitals to orbitals based on a Cass calculation, so that are by themselves like much superior, but the total wave function energy, dramatically error goes up. So roughly you get a 5 times increasement in the energy error. And then if you do like some minor changes, for example, you switch back from difference features to the distance features, and use the cusp correction, you end up more or less at kind of the energy error that PauliNet does. So it's really quite remarkable that building in some solution that is in principle a better starting point makes the optimization much, much harder. It's much harder to get like a really good description of the wave function if you start from something that's approximate but not quite right. And also like if you look at kind of the training curves, it actually happens very, very quickly that you kind of outperform a model that's based on something that's in principle rather good, but just after like 1,000 steps or so, you're already like much below kind of the accuracy you would reach with a Cass ansatz. Okay, how much time do you have? Maybe just like very quickly to touch on that. You might think this is an issue only if you bake these orbitals into the ansatz, right? Only if you kind of have as part of your ansatz like Cass orbital and you multiply it. So what we tried is we take an ansatz that just has the exponential decaying orbitals. So it's not kind of limited structurally by Cass. But then we pre-train it to look initially like orbitals from a Cass calculation. And we do it kind of both pre-training at one point to like Hartree-Fock, like a lower level theory, and we try to pre-train against Cass. Then we do variation optimization and we compare kind of the final results. And we can see is like in total the energy error, if you pre-train to a Cass calculation, which should in principle be better like a starting point, your final energy you will get after variation optimization can actually be worse than pre-training to a Hartree-Fock calculation. Like very, very weird behavior. Also, if you think like, how long do I pre-train? You think, well, the longer I pre-train, the closer kind of my starting point is already to like a reasonable wave function. And like as you do pre-training, kind of the energy of your, yes, please.
So I've heard this thing pre-train a few times, but I don't actually know.
Oh, sure. Yes, yes. So usually we do variational optimization. So we calculate the local energy and do unsupervised optimization of bringing the energy down. What you can also do in principle is, if you have a reference method, you can do supervised drilling, right? Have your wave function match some reference. And if you do that and you train long enough, in principle, you should reach also the energy of reference method. The reason why you might want to do this is, first of all, you can kind of make optimization a bit more stable because you start somewhere where the wave function looks roughly right and you can sample from something that's roughly right. And also supervised pre-training is much, much cheaper because you don't need to evaluate the energy, you don't need second-order derivatives. So that makes this much cheaper. Yeah, should have explained, thanks. Yeah, and you would think if you pre-train for longer, right, that kind of you get to a point where you better match kind of reference wave function with a good starting point, and if you then do variational optimization, you'll do fine. But actually, if you train longer and longer, I mean, initially your energy goes down, but then if you pre-train longer, you actually go up again in energy. A really weird phenomenon. Cool. So far for kind of this first part. Now I want to switch gears a bit and think about, well, what happens if we want to learn more than just one energy? I mean, there are many cases where we'd want to look at like total potential energy surface, let's say 100 of different geometries. And then the neat thing to do is, well, you take one geometry, you take one wave function model, you optimize it, you get one energy, and you repeat until like your potential energy surface. But this is like really, really expensive. Every one of those calculations is already expensive. Doing hundreds of them, often intractable. So how can you circumvent this? I mean, the one kind of obvious approach, I'd say, that we have heard a few times is, well, just do a few of those calculations and then build some supervised model that hopefully manages to predict your high accuracy beam calculations, and then evaluate that one on all the rest of the geometries. And that's nice. That's a perfectly valid thing to do. But first of all, then you only get kind of the predicted energies model. You don't longer have access to the wave function, which is a nice thing of VMC, that you get the full wave function. You can evaluate any property. And also just building this training set might also be like prohibitively, right? Even really good methods will need often hundreds of examples to properly learn the potential energy surface, and doing hundreds of those VMC calculations might already be too expensive. So one thing that we tried out is, what if you had these separate wave function models, but you share most of the neural network weights between them, so that you don't have to redo everything all the time, but you somehow kind of amortize the effort. So the architecture we used for this work was based more closely on kind of the polar architecture, but doesn't really make a huge difference. The big thing to note is we again have this like large embedding that takes in electron coordinates, spits out those high-dimensional embedding vectors, and then some kind of smaller parts afterwards that assemble like the full wave function. And what we try is that all the weights of the neural network that sit in these embedding parts, also some of the other parts, we share across all geometries. So if we do multiple molecules, they will all be forced to have the same weights. And then there's a few weights that are geometry specific. For example, if you had molecules with different sizes, right, you would need different size determinants. So maybe also like the backflow factors would need to be different to capture that. And then when we optimize these networks, we pick one geometry. We optimize all the weights, one step of that geometry. We will do gradient updates to kind of all the shared weights and all the geometry-specific ones. We pick the next wave function and go in a round-robin fashion. And the nice thing about this is that now all the shared parameters, they get much more gradient updates, right? Because you get the individual weights get one update kind of per geometry, but the shared weights get updates in no matter which geometry you optimize. So we tried this out for the example of ethylene, where we start ethylene, we stretched it a bit, twisted it, also to the point where kind of you have this transition barrier, which is difficult to sample. We took 30 different geometries, and at first we did VMC kind of the regular independent way, one after the other. We optimized the weights, and we need on the order of 16,000 training steps per geometry to reach chemical accuracy, like here defined as 1 kcal per mole. But then if we do the same thing using weight sharing, so sharing the embeddings across all different geometries, we get down in energy much, much faster. And only after around 1,000 geometries, 1,000 steps per geometry, we reach same accuracy. So we get the speed up on the order of like 16. Or in other words, basically you get kind of the whole potential energy surface of these 30 molecules. You basically get it for the cost of just doing 2 calculations, right? You kind of, instead of,
Hang on, when you're doing 30 different geometries,
yeah.
You need to do some training for each geometry at each step, yeah? I don't understand how it gets faster when you're trying to do 30 different geometries.
So it doesn't get faster in total. It gets
because
faster.
You've got to multiply by 30 that you haven't told us about.
So
right?
the total thing is like the total cost is kind of cost per geometry, well, times 30, yes.
Yeah.
So kind of this, to get all the 30 geometries, this one costs 30,000 steps in total.
Right.
This one costs, what is it, like 500,000 in total.
Right. So you've actually got a factor of 2 increase
Exactly.
in total, but you're doing 30 geometries.
Exactly like this.
Yeah.
That was the point, exactly. You have twice the cost, but you basically get 30 times kind of the output. And that works reasonably well also across different systems, right? I've shown you ethylene here. You can do the same thing for hydrogen chains. You can like stretch and distort them, and you get some speedups there. Smaller hydrogen chains, some hydrogen clusters. We've tried mostly small systems here because like calculations are still really expensive, but it seems to like work reasonably well across systems. The other thing you can do, which I find even a bit more exciting, is that if you train in this fashion, then your embedding has been somehow forced to learn something that generalizes across geometries, right? You have now one embedding that needs to do well across all the different twisted versions of ethylene. So what you can hope to do is that you do this shared optimization, you pre-train this, you get like your one big shared embedding, and you can now try to apply it to new geometries that have not been in the original training set, and see, well, if you initialize with kind of this embedding and train from there, how well are you going to do? And it turns out that you again, reach kind of chemical accuracy for these systems like really, really fast. So if you use these kind of embeddings that have been pre-trained on some shared data set of geometries, you only need, instead of like tens of thousands of steps to get to accuracy, you need only order of like a few hundred steps. So we're starting to become a bit closer kind of towards the number of steps that you would need in maybe classical or conventional variational Monte Carlo. I mean, still to keep in mind, it's like, this is not magic. You're still originally pre-trained on 30 different molecules for many steps. So, I mean, this is not magical that it works, but it's still kind of cool that you can transfer also to new geometries that's not seen. So you somehow generalize a bit in this embedding. Now, what I show you here is how you do if you go to different geometries of the same molecule. You can, in principle, also go to different molecules. You can, in principle, learn a wave function for, let's say, a hydrogen chain consisting of 6 atoms, train the embedding on a bunch of different geometries, and then take this embedding and transfer it to a hydrogen chain having 10 atoms each. And if you do that, so blue depicts kind of the naive independent optimization for hydrogen 10. The violet is what you get if you pre-train on other H10 chains. Well, that works really well. And the red one is kind of intermediate if you pre-train on H6 chains and then go to H10. So speedups are not massive, but it helps a bit, which is kind of nice. It's at least some hint that you can generalize those things. And we also tried it like for going from methane to ethene with very mixed results, I'd say. I mean, it helps a bit, but ultimately you kind of still need the same number of steps to reach chemical accuracy. So I'd say this is in principle like a really promising route to pursue. I mean, this is clearly not, we're like clearly not there yet. But if you like pursue this a bit further, ideally what we're dreaming of is that you could have at some point some like front end, let's say, of the wave function, like the embedding, that somehow has been trained on a bunch of different geometries and is like really general, and hopefully kind of get good feature vectors to then build wave functions for principal arbitrary molecules. So kind of, in a sense, like GPT-3 for wave functions, like in other domains like language processing or image processing, I mean, this is the way it's done. You pre-train kind of models on huge amounts of data set, and then if you want to do applications, you basically just put some kind of small head on top. I mean, maybe this is some way that could eventually also work here in quantum chemistry. So with that, I'm already towards the end of my talk. I hope they could all convince you that neural network wave functions are really quite amazing. I think it's early days yet. I mean, first papers on this have been written like only a few years ago, but already accuracy-wise, we're basically already there, or in many cases surpassing accuracy you get from other gold standard methods with decades of development. Optimization is still really slow and painful, but I hope I could also show you that there are ways to improve it. And I mean, both accuracies and kind of speed of these methods is picking up rapidly, kind of from paper to paper. There's sure much to be done in terms of better architecture improvements, or we made some improvements here, but there's for sure much to be gained also in improving how we structure these neural networks. The second interesting point I hope I could make is that it's not totally obvious that kind of delta learning works in this context. So while for potential energy surface, delta learning might be really, really great thing, it seems here that kind of in this case of wave function optimization, starting from some better method and then distorting this might actually be harder than starting from something simple but smooth and then learning the wave function from there. And the last promising thing, I think, is that you can also generalize wave functions across multiple geometries and maybe even across molecules to kind of get at some point, hopefully, some kind of universal wave function that approximates, in principle, anything you throw at it. So with that, I'd like to thank all the people who worked on this group, in particular my advisor, Philippe Gros, and Leon Gerard. Another PhD student has been working with me on this, who actually is here in LA, but due to COVID, unfortunately, spent all of the IPAM workshop at Luskin. But yeah, thanks so much to the entire group. Check out our papers. Also, all our code is open source, so yeah, check it out, and looking forward to your questions.